Hello students, welcome back. We only have one more section to go, and in this case, it's about piecewise defined function. If we have piecewise defined functions, typically we have these kind of possible breakings all over. So the derivative computation will be a special challenge. The best way to handle it is to use Newton quotient. It always works, even though it's hardest. Okay, let's calculate the derivative using the Newton quotient for the left-hand side. Remember here, h going to 0 minus. Let's increase the font. 0 minus. Oh, everything is increased, so it's a little bit hard to see. I'll just take this and increase this font only. Oh, sorry about that. Wrong key. Okay, alright. Even more. Okay, 0 minus. So h is a little bit less than 0, so 1 plus h is a little bit less than 1. Alright, let's go back to this. A little bit less than 1. Which line is it? First line, second line, third line. A little bit less than 1. So it's the first line. Now equal to 1, then function value is 3. So this is 3, so that's easy. So this is 3. So that's easy. Now how about this one? X squared, so 1 plus h squared plus x, so 1 plus h plus 1. There you go. That's the computation associated to 0 minus. So left-hand side derivative. That's too big. It don't have to be that big. I want to emphasize the 0 minus. Yeah, this is large enough. And then let's calculate this. The numerator here, let's break everything up. Break the complete square. 1 plus 2h plus h squared, and then 1 plus h, and then minus 3. And then what do you see? Plus 1, and then minus 3. I'm missing something. Yeah, this one. Okay, sorry about that. I missed this plus 1 here. Now it's back. Consequently, we have plus 1, plus 1, plus 1, minus 3. So the constant terms, they're all gone here. What's left? Just h terms. So that plus 1 is gone. That plus 1 is gone. This plus 1 is also gone, and so is this minus 1. And that's what we have here. Looks like I can simplify further. This 2h plus h, I can rewrite as 3h. And then we ended up with a 0 over 0 type limit. How do you handle that? Factor h out. We have 3 plus h, and then divided by h. Oops. Okay, there you go. Numerator is factored out like this, and then this h and that h divide each other out, and then we have this limit of 3 plus h, and that's 3 plus 0, because h is going to 0 minus. And yeah, 3 plus 0, I mean. Consequently, it's 3. All h expression will be gone because I'm plugging in h equal to 0 in the end. Make sense? And that's for the first line, x is less than 1. Now let's do the same thing for the third line, when x is greater than 1. That's what this derivative computation is all about. Let's increase the font. Yeah, we have 0 plus. So 1 plus h here is a bit greater than 1. So that's the third line. Let's see, f of 1 here is the second line, so that function value is 3. No problem there. And this one here, we have to use the third line. And this entire thing is, let's see, negative of x squared, so 1 plus h squared, plus 5 plus h. Excuse me. 5, 1 plus h, minus 1. And that's the expression by plugging in x equal to 1 plus h. Please check. And then let's break up everything. Let's see, breaking up this complete square, negative 1 minus 2h minus h squared. And then breaking up this 5 times 1 plus h, 5 plus 5h, and minus 1 again, and minus 3. Let's see, this minus 1, and minus 3, so that's negative 5, and here's positive 5. So all the constant terms, they're all gone. What's left is just h term. So that's gone, and then that's gone, and then all these are gone. Oops, excuse me. And then we have to have this limit expression. So what do we have here? We have a 0 type over 0 type limit. Numerator is 0, another 0 there. And let's see, negative 2h plus 5h, so it's plus 3h here after further simplification. And then factoring out, let's factor h out. So negative h plus 3. And then we can remove this h and that h. They divide each other out. And what do you have? Negative h plus 3. So if I plug in h equals to 0, 0 plus 3, the answer is again 3. That's the right-hand side. What do you have? The left-hand side's derivative, 3. The right-hand side derivative, 3. They're the same. So that's the same Newton quotient. The left-hand side limit of this Newton quotient, the right-hand side limit of the Newton quotient, they're the same. So the limit exists. Left-hand side limit and right-hand side limit both exist, and they're the same, so the limit exists. The common value is a derivative. Let's summarize all this. Left-hand side derivative is 3. The right-hand side derivative is also 3. So the derivative exists, and the derivative value is 3. As for the previous computations, let's see, the right-hand side derivative computation. Here, the same thing we saw before. That's for the third line, using the third line. And then, here's the same computation we just did. And that's for the first line, using the first line. The conclusion. And finally, a visualization. What do you see? It's a continuous function. Yeah, it was designed that way. If you plug in x equals 1 here and x equals 1 there, both will be 3, as in the second line. So we have a continuous function. We have no breaking there. Not only that, they're joined smoothly, so we have the same slope here. To the left, we have slope 3. To the right, we also have slope 3, so they extend into a single line. The same tangent line here. Okay, all right. Now, that's a perfect way, but in many cases, maybe not all, but in many cases, a shortcut solution is available. How do you do that? Instead of calculating Newton quotient, we can simply take the derivatives. So the derivative is, now this middle line is meaningless. Take the derivative. 2x plus 1. If you use a derivative formula here, do you get that? And then take the derivative here. Negative 2x plus 5. If you use the derivative formula to the third line. Now, when I plug in x equal to 1, what do you get? Plug in x equal to 1. 2 plus 1 plus 1, that's 3. Plug in x equals 1 down here. Negative 2 plus 5, that also is 3. So you don't really have to separate like this, and then it works only for strict inequality. It works for semi-inequalities as well, because they have the same value, you see. And the derivative evaluated at x equals to 1 is either from the first line or third line. We get the same value. F prime of 1 is 3. Maybe I'll rewrite like this. Yeah, 2x plus 1. And then negative 2x plus 5. And let's remove some space here. And then that's for f prime. Okay, it'll work. Because the common value as we calculate turned out to be 3. Remember that? Yeah, either way we got 3. We happen to have the same value 3 here, but that's rather coincident. That's rather coincident. Either this way or that way. Doesn't matter which way you do. Okay, we went through the shortcut method as well. You can apply the derivative formula for the first line, third line separately, and then check if you get continuity from there. Plug in x equal to 1, plug in x equal to 1 if they meet. Most of the time, it'll work out. In order to create a counterexample, then we have to have some discontinued function, and that's going to be weird. Still, there's no question that this Newton quotient method is the best, because theoretically it is sound and it always works. But for exam purpose, for example, the shortcut method is quite useful. Okay, so much for the first example only. Oh wow, we have 3 more examples here. Oh boy, how am I going to do that? Well, let's meet again soon.